So last time, the last two lectures we've been talking about vector bundles, and last time I introduced these tautological bundles, which remember are vector bundles over Grassmannians. So if GR, K, N, F is the Grassmannian of all planes of linear subspaces of dimension K inside F to the N, that's a Grassmannian. And then we can define a canonical vector bundle over this Grassmannian. The way we think of it is that it's a subbundle inside the trivial vector bundle. And it's tautological in the sense that it is equal to a set of a plane and a vector such that that vector fits inside that k-dimensional space. While it's tautological, it's not trivial, and so last time we spent some time looking at the one-dimensional case. So then these are one-dimensional vector bundles over projective space. And we analyzed in some detail already the case n equals 1 is not trivial. So if we take n equals 1 and f equals r, we get the Mobius bundle over the circle. If we take n equals 1 and f equals c, we get what I call the magnetic monopole bundle. It's a complex line bundle. And if we take E inverse, call that H, then that's also got a name. That's the hyperplane bundle. And we showed that very beautifully this H is a holomorphic line bundle, H to the K. If it's a holomorphic line bundle over CP1, we identify CP1 with a two-dimensional sphere, take the usual stereographic projections as the complex numbers, then sections of this are given by a holomorphic function S plus on the northern hemisphere, which is related to S minus on the southern hemisphere by C plus to the K. And so when K is greater than 0, greater than or equal to 0, there exists a K plus 1 dimensional space of holomorphic sections. And we'll be saying much more about those. Finally, if I take n equals 1 and f equals the quaternions, I get a certain rank 2 complex vector bundle over S4, which is associated with instantons. All right. We also talked a little bit about twisted bundles and other nice things. Now today, I'm going to talk about a general construction called the associated bundle construction. Okay. So we have talked at some length about principal bundles. So the fibers of principal bundles are Lie groups. We have also talked a little bit about vector bundles. Okay, so the vector bundles, fibers of vector bundles are vector spaces. And the associated bundle construction is going to relate these two. Let me state it more generally for as follows. Suppose we have a principal G bundle, let's call that pi sub p, that's a principal G bundle over M. And suppose also, so that's one thing we have, and suppose the other thing we have is F is any space with a left G action. Then we can form the associated bundle. Okay, so it's going to be a bundle over M with fiber F. And the construction goes as follows. We note that there's a fixed point free left G action on P times F. Okay. So let's denote that A sub G. There are a lot of G actions around, so I'm giving this one a name. A sub G, which by definition is P G inverse G dot F. Okay. Now remember that a principal bundle always comes with a fixed point free right G action. By putting the G inverse here, I'm making that a left action. And then this is just some abstract left G action on this space, capital F. Now, this being fixed point free, we can take the quotient, and that defines the associated bundle. It's usually written this way. P crossover GF is by definition the quotient space of P times F by this equivalence relation. So I'll denote points in here by equivalence classes with a square bracket like that. So little p is a point in big P, and little f is a point in big F. Okay? And so this equivalence relation means that this is equal to P dot G inverse G dot F. Okay. Now there's another way of thinking about this equivalence relation, trivially related to this, but still sometimes more useful to think about, is that if you take P dot G comma F, that's the same equivalence class as P comma G dot F. Okay, now there's a natural projection from this down to M, where we take pi of the equivalence class and simply set that equal to pi sub p of p. And you see that's well defined. We don't quite know what p is because we could multiply it by g, but that's exactly what we quotient out by when we take the projection of our principal bundle, capital P. Okay, now I leave it to you. It's actually spelled out in detail in the notes, which are on the way. I leave it to you to verify that the fiber of this projection is indeed F. So exercise. If I take pi inverse of some M, then that is indeed a space which we can identify with F. So what I've done here is I've gone from a principal G bundle, where the fibers are some group, to some other bundle, where the fibers are the space F. Now maybe it's worth saying, how many people have seen this construction before? Okay. So it's worth saying in a little more detail what the transition functions of this are. So suppose that we have phi alpha and u alpha and g beta alpha, all of that stuff, trivializations, Willing data for capital P. Then we automatically get a set of trivializations for the associated bundle as follows. So we naturally have trivializations of this space here, right? Because this is just a cross product with F, and we've got a trivializations of P. So we certainly have those. And specifically, phi alpha inverse of P comma F is phi alpha inverse of P comma F. Now, I'm using phi alpha for slightly different things here, but the notation would get ridiculous if I put an extra tilde or hat or something on all the different phi alphas, which are slightly different from each other. I hope that won't cause confusion. Now, using the definition of the right G action in terms of local coordinates, we see that this indeed descends to equivalence classes in a well-defined way. So supposing this is xg comma f, then by our equivalence relation in this form here, remember this is x1 right action by g, so this is equal to x comma 1 g dot f. Okay. So what we can say is that if the local trivialization for P is phi alpha inverse of P is x comma g, then the corresponding local trivialization for the associated bundle, P crossover GF, is phi alpha inverse of this equivalence class is x comma g dot f. Okay, you see, this is in u alpha times f. This is in u alpha times g. Okay, that's what we learned from this. Okay, so we've got a trivialization of our associated bundle, and let's just calculate what are the transition functions. If the transition functions for P look like phi beta, phi alpha inverse, which remember goes from u alpha times g to u beta times g, and specifically takes a point x comma g goes to x comma left multiplication. So the g beta alpha of x's here are the gluing functions. Then the corresponding gluing functions for the associated bundle take phi beta phi alpha inverse from u alpha times f to u beta times f, and are given by x comma little f goes to x comma g beta alpha of x dot f. looks easy enough, right? But bear in mind that the notation here is somewhat abstract. This is just some general left G action. And then here are the notes. 2 cents. All right. Now, a particularly important special case is a case where F is V, a representation of G, a linear representation of G. So in this case, I might denote little f by a vector V in G, and G dot F would mean rho of G, the representation linear operator acting on V. So those would be associated vector bundles. Okay, so that's the abstract nonsense. Okay? Let's look at some examples. So example 1. Suppose that we indeed take rho is the trivial representation. Okay? On a vector space V. So it's just completely stupid. Then P cross G of V is simply P mod G times V is M times V is the trivial bundle. You see, because in this equivalence relation, if I have the trivial representation, then this is not doing anything, so I'm just quotienting out P by G, and that's M. Okay, so let's go to a more interesting example involving these tautological bundles. So, remember a long time ago we talked about the principal bundles over projective spaces given by F star. And let me remind you again that coordinate patches for the projective spaces are given by homogeneous coordinates bi1 through bi n plus 1, such that we set bi I equal to 1. So that's a copy of Fn. And then we have over on uij, we have bik is bjk times bi sub j. Okay, those are the transition. Those are the coordinate changes. Okay. Now we could take a one-dimensional representation for rho. So rho takes F star to F star acting on F. Think of that as a one-dimensional representation of F star. So this is my principal bundle. Here's my representation. And then the associated rank 1 bundle. Well, by what I just said right over here, we know that it has transition functions Vj equals Vi times Bi sub j. Right? Same as the left action, as the right action, as the gluing functions we had before. And therefore, the associated bundle, this is just the one-dimensional bundles that we talked about last time, because last time we found that these tautological bundles have exactly these transition functions. Now, in a way I'll make precise in a moment, these also are topologically the same as the bundles where we take F star to the unit norm elements. Right, so that means that we take the multiplicative group of non-zero real numbers to Z2, the multiplicative group of non-zero complex numbers to U1, and the multiplicative group of non-zero quaternions to SU2. And then in that case, these bundles here are topologically the same as what we saw before, Z2 Sn over Rpn, U1 to S2n plus 1 over Cpn, etc. And so then we could use the, we could associate to these principal bundles real and complex line bundles. Now, indeed, let's focus on the complex case, and let's simplify our life by thinking about n equals 1. So then we're talking about our good old friend, the Hopf fibration. Now, recall, for the Hopf fibration, we discussed that in great detail. So we have SU2 over SU2 mod U1. It's a principal U1 bundle. And I'm not going to go through all the details of that. We certainly went through that in great detail. But I'll remind you that, again, with stereographic projection and a suitable choice of fiber coordinate, which we called e to the I chi, we found that e to the I chi on the north pole is e to the I phi times e to the I chi on the south pole. Those are the transition functions along the equator. So over here, we have a fiber coordinate e to the I chi north. Over here, we have a fiber coordinate e to the I chi south. This is phi, and these are the transition functions. So we discussed that principal bundle in great detail. Now, let's look at representations of U1. Well, natural representations of the group U1 take rho sub k, which takes e to the I phi, goes to e to the I k phi, where k is an integer. Okay. That's a one-dimensional representation. The representation space V is equal to C here. And then what are the transition functions of the associated bundle associated to this representation? Well, the sections would be given by functions S plus from U plus to C, S minus from U minus to C, such that S plus is equal to e to the I k phi S minus on U plus minus. So if we were e to the I chi north, I could also call e to the I chi plus, e to the I chi south is e to the I chi minus. Well, those are complex line bundles over the two-sphere, which are indeed the ones we associated by taking this tautological bundle to the minus kth power. So this is E12 of C to the minus kth power, which was L sub k, which was S sub k, as a complex line bundle with structure group U1. Similarly, for the instanton bundle, Now, the representations of the instanton bundle are a little more interesting, right? Because for the instanton bundle, we have a principal SU2 bundle. Goes into S7 over S4, which is HP1. And we saw that so the tautological bundle, E12 of H, had C, let's see what I call it, C minus 1, C minus 2 is x4 plus I x dot sigma on C1 plus C2 plus. So that was where we considered the 4 sphere to have stereographic projection to R4. And then we would look at representations of SU2. So let's call that rho sub j. So we take an SU2 matrix, raise it to the jth power. We take the symmetric power. So we would have the jth spin representation, and so then we would get bundles that look like psi minus to the j over 2 through psi minus to the minus j over 2 is some rho j of x4 plus I x dot sigma psi plus to the j over 2 psi minus to the minus j, psi plus to the minus j over 2. So those are coordinates on a vector bundle whose rank is 2j plus 1. And these would be the transition functions on the equator, which we can identify with SU2. And so for an element of SU2, we can take the spin j representation. So that's what the associated bundle construction would do for the instanton bundle. Okay? Any questions about that? Okay. Now, one more formal thing I want to do is talk about sections of associated bundles. Okay, so we have this situation that we have a principal G bundle, and we have a G space F. And in this situation, we can look at the maps from P to F. Okay? And I claim that this space of maps has a right G action. And what would that be? Well, suppose I have a psi, which is a map from P to F. So given an element little g, in G, I need to define a new Rg of psi, goes from P to F. Now how will I define it? Well, I'll define it by saying that the values of Rg of psi at P is equal to G dot psi of P dot G. Okay, so there are a whole lot of G actions here. This is the right action of G on the principal bundle. So this is a function on a principal bundle to the space F. This is the G action on F. You see, psi of this thing is in F, and so G can act on it. Okay, you can check that this is a right G action. Now, the grand tautology of this subject identifies the sections of the associated bundle with the maps from P to F, which are invariant under this G action. So let me say that really slowly. So sections of P times G, the associated bundle, over M, so we're talking about the sections of this, is canonically identified with the space of maps from P into F, which are invariant under that right G action. So let me write that out. That's the set of all maps psi from P to F such that psi of P dot G is rho of G inverse psi of P. Now, let's understand. Is that obvious to anybody? I think it's not obvious if you haven't seen it a number of times before, but let's try and make this really, really obvious. So what are we doing when we give a section here? Well, what we're doing is for each x in M, we give an element in the fiber. And what's an element in the fiber? Well, we give this equivalence class, let's call it P sub x, F sub x. Right? But, okay, so P sub x is in the fiber of capital P above x. But we can, what is the equivalence class? It's a set, right? It's equal to the set of Px dot G, comma, G inverse f sub x. It's a set of points inside P sub x times f. Let's regard that equivalence class as the graph of a map from Px to F. In other words, you have Px here, you have F here. As we go along Px, remember Px is the torusor for G. So for every P sub x, I'm giving you an F sub x. You see? So this equivalence class is a graph of a map from P sub x to F. And, okay, so that's a map. Okay, so we have a map from Px to Fx. Let's call that psi. That's going to be our psi. Now, what do we know? We know that the equivalence class Px dot G, comma Fx is equal to the we know that Px dot G, comma G inverse, or I guess I should. Okay, nobody caught me on that. Rho, I was denoting the left G action on F just abstractly as G inverse dot F. Here I made it, I was thinking really of the vector bundle case. I should have just written to be consistent with what I said before. G inverse dot psi P. Okay. So we know that Px dot G, G inverse dot Fx is the same as Px Fx. But what does that say? this says that psi of px dot g is g inverse f of x. But what is f of x? F of x is psi of px. Right? So these are just the equivariant functions. Okay, I have a discussion in the notes where I further beat this into the ground by going to a local trivialization, but I think maybe you got the point by now. So this is what I like to call the grand tautology. The sections of the associated bundle are nothing more or less than they're equivalent to the equivariant functions from P to F which satisfy this equivariance condition. Are there any questions? Yep.
Well, so in principle, one could make a good choice and build the associated bundle onto, by placing, let's say, fibers onto a smooth section, at least locally, on the principal bundle.
Say that again?
So if one considers local smooth sections on the principal bundles and literally places fibers above that section, one can build up locally the associated bundle in that way.
Yeah, that's kind of the way I was constructing the local trivializations.
So,
But then you have to mod out.
yeah. No,
Because in the associated bundle, you mod out. It's P times F mod G.
But if we take a section on the principal bundle,
Yeah.
then we already modded out.
No, you chose some zero for your torsor.
Yeah.
But to mod out, you have to quotient out by that whole. So if I'm understanding you correctly, you know, I took this, but then I modded out by G. So you see, points here are x, comma, g, comma, f, but then the equivalence relation is that this is x, comma, 1, comma, g dot f.
No, actually what I was saying is if we take a section on the principal bundle, we have 1 point on each fiber. So we
have a point in the principal bundle.
Yes, and over that we have a fiber of the associated bundle. That is. So in that sense, it's a way.
No, I'm not following that. Sorry.
Oh, maybe I can't. Sorry.
Okay, that I'm not following. Okay, so this is all very abstract. So I think what I'm going to do is change order a little bit from the notes. So in the notes I went on to talk about the frame bundle and reduction of structure group. I'll come back. That's also very abstract. And I think I better instead first tell you about something a little more concrete where we really use this associated bundle construction, which is the theory of induced representations. And we'll come back to frame bundles and the reduction of the structure group later. Now, induced representations, you'll soon see the relationship to associated bundles. This is a very beautiful chapter in representation theory, which is already non-trivial for finite groups, gives a rather lovely unifying point of view for representations of all compact Lie groups, which is sometimes known as the Borel-Bach theorem. It has a generalization to non-compact groups. And in some sense, those of you who have taken field theory have already seen an example of this, because it's the proper mathematical framework for describing the Wigner construction of unitary representations of Poincaré and also superconformal, supersymmetric, etc. groups. If we had a lot more time, I would certainly spend a lecture or two explaining the unitary representations of Poincaré groups. It also puts a nice perspective on what are called coherent states and representations of Heisenberg groups. And in the latter half of the notes of this chapter, I do explain some things about Heisenberg groups. We won't have time to talk about that, but I'll hand that out next time. And it also generalizes rather beautifully to loop groups. So it's a very general and useful construction to know about. So how does it go? Well, suppose that H is a subgroup of G. Okay? H and G are just some groups. And suppose that rho goes from H to the general linear group of V is a representation of H, not of G, of H on a vector space V. Well, when we have a subgroup H of G, we get a principal H bundle. We take H into G, and the quotient is homogeneous space G mod H. So that's a principal bundle where P, the total space of my principal bundle, is the group G. Now, okay, so we have a principal bundle, a principal H bundle, and we have a representation of the structure group. So we're in exactly the situation I had before, where we can form the associated bundle. Which we'll now denote as G times over H V. So that's a vector bundle over G mod H. So my associated bundle is a vector bundle over G mod H. Now, we can therefore study the sections of this vector bundle. And then, by definition, this is the induced representation from H to G of V. Okay, now let's write out what that means according to our grand tautology, and let's see why that is a representation of G. So you see, we start with a representation of H, we get a representation of G. So, using the tautology, we can identify the induced representations, the space of the induced representations, to be equal to what? So their functions, psi from G to this V, such that psi of GH is rho of H inverse psi of G. You see, that makes sense, right? I'm saying for every G, I'm getting a vector V in this representation space for H. And I'm making it equivariant in this way. So if I right multiply by H, I get the action of H inverse on psi of G. Okay, so that's certainly a vector space of functions. If I add two such functions, I get another one. It has the same equivariance property. If I multiply it by a scalar, I get another function with the same equivariance property. Why is this a representation of G? This is a representation of G because I can define the following action of G on such a function psi. T of G dot psi will be the new map such that its value at G prime, by definition, psi of G inverse G prime. Well, that makes sense because psi is a function on G. And now I leave it to you to show that this is a good left action on the space of functions. Namely, this is true. It's a little calculation you can do. And one thing we better check is that if psi has this equivariance, then so does T of G dot psi. So let's check that. So what do we want to check? So T of G dot psi, we want to see what's its value on G prime dot H. Okay, well, this is by definition psi of G inverse G prime H. Okay. But on the other hand, by the equivariance of psi, that's just rho of H inverse on psi of G inverse dot G prime. Okay. But that's equal to rho of H inverse on T of G dot psi evaluated at G prime. And that's exactly what I wanted to establish for my function T of G dot psi. So that means that T of G dot psi is also equivariant. So with this G action, we have a map of the space to itself, which is linear. And so that defines a representation for us. So let's think about what does this look like for finite groups. So example 1, G and H are finite. The geometrical ideas still apply. Right? So G mod H is a finite set of points. Finite set of cosets. And over each of these cosets, let's call it G sub J H, over each of these is a copy of H. So it's an H bundle over this finite set of points. So we can certainly talk about induced representations and think about them geometrically. So what do we have here? So let's let rep of G be the category or set, if you're scared of categories, the category of all finite dimensional representations of G, and similarly for H. And if you think, if you're not scared of categories, then the Hopf spaces in this category is what we might denote Hopf of G of W1, W2, which are the intertwiners, that is, the linear transformations from W1 to W2 commuting with G. So what the induced representation construction does is, let me just call it IND. I should be writing sub H upper G, but I'm going to suppress that. So the induced representation construction is giving me a functor from the category of representations of H to the category of representations of G. Now, on the other hand, there's an obvious functor going the other way. Let's call it R, from the category of representations of G to the category of representations of H. And that's just given by restriction. You see, if you have a representation of a group G and you have a subgroup H, it's obviously a representation of H. Okay? Clear. Now, so we could ask, how are these related? And the beautiful answer of Frobenius Reciprocity is that these are adjoints of each other. In the following sense. So this is the Frobenius Reciprocity theorem. It says that the intertwiners between W and the induced representation from V is the same thing as the intertwiners, in the H sense, of the restriction of W and V. So look what's going on here. So W is a G representation. V is an H representation. So the induced representation takes a H representation and gives you a bigger representation, a G representation. So it makes sense to ask, if W is a G representation and V is an H representation, what are the linear transformations commuting with G, the intertwiners between W and the induced of V? Over here, V is an H representation, and W can be, of course, restricted to an H representation. And then we can ask, as H representations, what are the linear transformations that commute with H? And now you see why I say it's an adjoint. You see there's an R star here on the W side. Over here it turns into an induced, so it looks like they're adjoints. Okay?
Sorry, what's R star?
R star is the restriction. Oh.
It's just R.
Yeah.
Can I ask a question?
Yeah.
So if you think of this as a representation ring, is this a ring homomorphism?
Pardon? Is it a ring homomorphism? Good question. I suspect the answer is yes, but yeah, because you see, think about, supposing we took a tensor product of these, V1 and V2. Yes, I think that's correct. Right, because if we think about psi goes from G into V1 tensor V2. So let's think about that space of functions. Okay. So you're asking, is that isomorphic to the tensor product of psi's which go from G into V1 tensor psi's which go from G into V2? And that looks pretty likely to me. There might be some functional analysis, subtleties if G is a non-compact group and stuff like that. But excellent question. I think that the answer is yes.
In the case of this Cartan business, that's true.
What Cartan business?
If you take H to be like Luxembourg.
Well, that's where I'm going. And yeah, so if they're compact, yeah, I'm a little worried about some subtleties in functional analysis, but for compact groups, I think it'll be okay. All right. So this is Frobenius reciprocity. So induction and restriction are adjoints of each other. Let me state this in another way, which might be useful, and I'm going to indicate a proof, and so it'll be easier to prove this other way of saying it. You see, you could ask, given an H representation V, you induce it to make a G representation, you could ask, well, how does that decompose in terms of its irreducible representations of G? So, how does the induced representation from H to G of V decompose with respect to irreducible reps of G? Well, Schur's lemma tells us the following. Let W alpha be the distinct irreps of G. Then the induced representations from H to G of V is, this is just Schur's lemma, of G of W alpha into the induced representation. So that's just Schur's lemma. Now, Frobenius reciprocity allows us to simplify this term here. So we get the sum over alpha of W alpha tensor the Hom over H of the restriction of W alpha with V. Now, why is that useful? That's useful because, you see, H might be simple and G might be complicated. H might be abelian and G might be non-abelian. So when you're dealing with the representation theory of abelian groups, okay, it's a lot easier to calculate intertwiners and things. So this is actually a big simplification. All right, now, how do we prove this? Well, we have this finite set of points, G mod H, and over any coset, we have a copy of H. So think of it geometrically. Okay? And so this is equivalent to the character of chi in this induced representation being chi induced of G is the sum over x in G mod H of, let's call it chi hat, of x inverse Gx, where chi hat of some G prime is equal to chi in chi sub V of G prime if G prime is in H, and 0 if G prime is not in H. Okay, so I leave that as a little exercise. And we'll simply prove this. How do we prove this? Well, let's enumerate the points in G mod H as cosets G sub J H. So J equals 1 through some integer n. And then we know that the left action has to look something like this. So make a choice. Choose a G sub J for each J. And then G times G sub J is going to be G sub G dot J times H of G comma J. What's going on here? G dot J goes to G dot J is just a permutation. Okay? So I'm just saying that if I make a left action by G, I go from one point here to another point here. That's the permutation action. So that's a permutation of the points of G mod H. Now, I just made some choice of coset, a representative for each coset. And that, you know, that's just a choice. So there's always going to be some compensating H transformation like this. If you do pion physics, if you do chiral symmetry, this kind of compensating gauge transformation comes up all the time. Since the pion field is like a choice of coset. Well, let me not go into that. So, okay, so now let's define a basis for the sections of G times H of V. Okay? So, introduce a basis, VA for V, and then define psi IA of G sub J to be VA delta ij. In other words, think of it as, for choosing an I, if this is the ith point here, I'm going to choose a section which only lives at that point. So it's supported at I. And then it's this vector VA. And then I make this equivariant in the way I know I have to. So this is equal to rho of H inverse VA delta ij. Okay, so I want to prove this formula for the character in the induced representation. So let's see, how do we do that? So let's calculate G dot psi IA. Okay? And let's calculate its value on some Gj. Okay, well, by definition of the G action, that's G inverse G sub J. Okay, by my choice of section of the G mod H of the H bundle over G mod H, this is equal to psi sub IA of G sub, this is awful, I know, G inverse dot J times the compensator, which is H of G inverse comma J. All of that. Okay, so it's moved me in where I am on the set of points, and then there's a compensator. Now I have equivariance. So this is, first of all, delta sub I, comma, G inverse dot J, and then rho of H of G inverse comma J inverse dot VA. Now that looks pretty awful. But fortunately, we want the trace. Okay? So this can be expanded in terms of these functions. But we're only interested in the coefficient which brings us back to psi sub IA. So that means that we're only interested in J equals G dot I. Okay, so first of all, this is only supported, is only non-zero when J equals G dot I, but we also want J equals I, okay? Because we want the trace. So we're acting on psi sub I, okay? And we only want the overlap with psi sub I, because we're calculating the trace. Now, psi sub I has the property that it's supported on G sub j for j equals I. That's the only place where it's non-zero. On the other hand, by our calculation, it's supported on j such that j equals g dot I. So, therefore, only the fixed points of the G action on G mod H contribute to the trace. Now, if G is a fixed point, then G dot G sub I is equal to G sub I times H of G comma I. And therefore, H of G inverse of I inverse is equal to H of GI. Thank God. Okay? And therefore, when I also take the trace by summing over the A, I get the V character of this H of Gij. So what I'm saying is, so chi of G is equal to the sum over fixed points of G acting on G mod H of the trace for that fixed point of in the representation V of G of H of GJI. But you see, H of GJI is equal to this thing here, and this implies that H of G comma I is GI inverse G GI. So this is the sum of chi sub V of GI inverse G GI summing over I in G mod H such that G dot GI H is equal to GI H. And that's exactly this formula over here. So that gives you a geometrical proof of this beautiful Frobenius Reciprocity theorem. Now, in the notes, I worked this out. This, again, probably looks pretty difficult and abstract. But in the notes, there's something else I want to do, so I'm not going to do it on the board. But in the notes, I work out an example. Simplest possible interesting example. I take H to be the group Z2. I take V to be just the one-dimensional representation where sigma is minus 1. Okay, the non-trivial representation of Z2. And then I take G to be the permutation group on 3 letters, so we could think of H inside G as a subgroup of permutations of 1 and 2. Okay, and I work out in detail what is the induced representation. Okay, and so the induced representation then from the permutation group on 2 letters to the permutation group on 3 letters by V. In fact, I do it for both cases. So sigma equals epsilon plus or minus 1. I work out this induced representation, and, well, it's some non-trivial sum of representations. It's a 3-dimensional vector space, and so it's the sum of a 2-dimensional rep of the permutation group, direct sum, a 1-dimensional rep of S3. And you can calculate that very directly by literally calculating the equivariant functions, or you can calculate it from the character. Or you can calculate it from Frobenius reciprocity. Okay, but time is running short, and I've got an important subject I just have to talk about right now. I want to talk about another example of an induced representation having to do with the magnetic monopole. Which is very, very lovely. So, let's now consider induced representations from U1 to SU2. Okay, so this is our G, this is our H. Okay, so as I said, the irreps, the unitary irreps of U1 are labeled by an integer k, rho k, instead of e to the I psi, we call it chi, is equal to e to the I k chi. And let's call the representation space V sub k. It's a one complex dimensional vector space. So then we can form, as I've already said in this lecture, we can form the associated vector bundle. And as a complex line bundle over SU2 mod U1, which we can identify with S2 or with CP1, as a complex line bundle over those spaces, this is what we called L sub k. So now I want to say, let's work out the space of C infinity sections of L sub k. Okay, so what is that? So those are functions, psi, which go from SU2 to V sub k, that's just the complex numbers, such that psi of G right action e to the I chi is equal to e to the minus I k chi psi of G. Now what's the right action on SU2? Well, to be consistent with our conventions for discussing the magnetic monopole bundle we had before, G dot e to the I chi, that's just an abstract notation, is matrix multiplication minus I chi sigma 3. Okay. So on the left-hand side here, I have an abstract right U1 action. On the right-hand side, I have honest matrix multiplication. Okay, so what are we doing? We're saying that gamma of Lk is the set of functions psi from SU2 to the complex numbers such that psi of G e to the minus I chi sigma 3 is e to the minus I k chi psi of G. That is the induced representation. It's induced from a one-dimensional representation of U1. It is now a representation of SU2. I want to ask, just like I'm erasing this statement we just asked the same question in general, I want to ask, what representation of SU2 is this? Anyone want to guess? What representation of SU2 am I getting? See, I start with this one-dimensional representation of U1, labeled by K. Okay? I form this thing. This is, by definition, the induced representation from U1 to SU2 induced from VK. Set of functions from SU2 to the complex numbers with this equivariance property, okay? Now, I've been throwing a lot of abstract stuff at you, but this is really concrete. Are there any questions about this? Okay, this is really concrete. So how are we going to deal with this? Well, in order to deal with this, we need to know something about the functions on SU2, obviously, right? What do we know about the functions on SU2? Well, we have the beautiful Pater-Weyl theorem. The Pater-Weyl theorem tells us exactly that L2 of any group G, any compact group G, is a sum over all the irreps of V rho bar tensor V rho as a representation of the left and right regular representations. This is the left regular and the right regular. Now we can apply that to SU2. So for SU2, that says L2 of SU2 is the direct sum from J equals 0, 1/2, 1, dot, 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 of the representation of spin J tensor the representation of spin J. Okay, so I think you all know the representations of spin J. The way we go from this abstract thing to a function on the group is we look at matrix elements. So if we're in the spin J representation, then we can take the matrix elements in that representation. These matrix elements are by definition something called the Wigner function. So this is some concrete function on SU2. Now, actually, let me put this over here. Now, the parameterization that we've used for the Hopf fibration looks like this. I'll remind you. So T of J of e to the minus I over 2 phi sigma 3 Tj of e to the minus I over 2 theta sigma 2. Phi and theta are the usual angular coordinates on S2. And we have T of J e to the minus I over 2 psi sigma 3 J m. Okay, so then this is going to be e to the minus I m left phi pj m left m right of cosine theta e to the I m right psi, where pj m left m right is the associated Legendre polynomial. Now, okay. So now what do we want to do? Under this U1 action, now you see, this U1 action in these Euler angle coordinates takes psi, goes to psi plus 2 chi. That's my U1 action. What do we wish to ask? We wish to ask that we have that equivariance under the U1 action. So this has suitable equivariance if m sub right, 2 m right, is minus k. That is, m right is minus k over 2. Okay? So now, in a sense, we've solved this. We figured out that the induced representation from U1 to SU2 for VK is the span of the Wigner functions dj sub m left comma minus k over 2. Now, what j's can occur? Well, clearly, if I'm going to have an azimuthal spin minus k over 2, I must have j is greater than or equal to the absolute value of k over 2. Otherwise, that azimuthal angle eigenvalue doesn't even occur. And then we have to have the proper parity. So here we have j equals 1/2 absolute value of k, comma, 1/2 k plus 1, 1/2 k plus 2, and so on. And of course, for each j, we have minus j less than or equal to m left, less than or equal to j. So those are the values of j and m left which can occur. Now, I forgot to mention, but with the natural unit norm Haar measure, these form an orthonormal basis of L2 of SU2. It's part of the Binomial Theorem. Now, the other thing I should remind you is that if you fix any m right, then the span of dj sub m left comma m right, where you look at the finite dimensional space where m left is goes between minus j and plus j, is isomorphic to the complex conjugate of dj bar. That's the dj bar here under the left regular representation. If you don't know that, that's explained in the notes, and I'll leave it to you to learn that. If you don't already know that, it's an elementary calculation. It's good exercise also. So, what have we deduced? That this, as a representation of SU2, is the sum over j prime greater than or equal to 1/2 absolute k with proper parity of d sub j prime bar. I have answered the question. That is what the induced representation looks like as a representation of SU2. It's infinite dimensional. Okay. You can check Frobenius reciprocity. You can check that hum SU2 of dj prime with the induced representation vk, the one I just wrote, you can check. You see it's got multiplicity 1, and it only exists when j prime is in this range here. And you can check that this is indeed the representations. If I take this representation of SU2, dj prime, and I restrict it to a representation of U1 and ask what are the intertwiners to do VK, that's a fancy way of saying when does dj prime have an azimuthal angle, which is, an azimuthal quantum number, which is equal to minus k over 2. Anyway, you can check that that's consistent with Frobenius reciprocity. Now let me make a tiny remark here. The first remark. Second remark, if k is equal to 0, L sub k is just the trivial bundle. S2 times the complex numbers. So then we expect, So sections are just functions on the two-sphere. So what are those? Well, so those are d, j, comma, m, 0. Right? These functions, when k is 0. Well, these have a name. These are called spherical harmonics. You see, because of the 0 here, the equivariance means they're independent of psi. It means they just depend on the azimuthal coordinates, theta and phi. So this is indeed a complete orthonormal basis of functions on the two-sphere. So that's a special case. The other guys are sections of bundles. They depend on psi. And in fact, it's another remark, in the quantum mechanics of a particle of electric charge 1 on a sphere surrounding magnetic charge K monopole, the Hilbert space of the electron would be the electron. Well, I haven't shown it because we've run out of time and I haven't done connections on bundles and all of that, but you'll have to trust me that if we did that problem, that quantum mechanics problem, we discovered that the wave function of the electron would have to be a C infinity section of exactly this line bundle L sub k. It has to be normalizable, and so the Hilbert space of the theory is this. Okay. I'm going to go a little bit longer. Yeah, because there's another aspect of this story that's really, really beautiful. So we've got this infinite dimensional representation. Now, you might be wondering, how is this related to the finite dimensional representations? By the way, if you were thinking of L sub k over CP1, you were doing some quantum mechanics on CP1, some supersymmetric quantum mechanics on CP1, you would then have n equals 2 supersymmetric quantum mechanics, and you could ask about Bps states. So what I want to describe is, in some sense, the Bps states. That didn't make any sense to you in the context of what I have said. We've been talking about L sub k over CP1 with structure group U1, right? I associated the L sub k right here. It's an associated line bundle to a principal U1 line bundle. But we observed last time that, if you look at the transition functions on the equator, it's the same as the transition functions of a holomorphic line bundle. Where we had S plus equals Z plus to the K, S minus is our transition function. So we could ask, what sections of L to the K correspond to the holomorphic sections of CP1 H to the. So we could also ask the question that way. Now, to answer this question, we need to complexify SU2. So if we complexify SU2, we get SU2 goes to SL2C. Actually, it'll be a little more convenient to go a little further and talk about GL2C. So I want to observe that SU2 mod U1, observe that SU2 mod U1, that homogeneous space, is the same as GL2C mod B, where B is what's called a Borel subgroup, and it's equal to the group of matrices of this form in GL2C. Indeed, I could define a projection from GL2C to CP1 by taking some matrix that looks like this, G11, G12, G21, G22, and I could map it to G11 colon G21. That's because, so the fiber I claim of that map will be the Borel subgroup, and to check that, you simply note that if you multiply a matrix like this times a matrix like this, then that's equal to a matrix like this. Okay, so you can do that multiplication right now in your head, check, and so that means that the fiber of this is exactly the Borel subgroup. Okay, so we can identify CP1, our complex manifold, as a quotient of complex Lie groups like that. Now, why is that useful? Because we can apply our associated bundle construction again. So now, let rho sub k from B to endomorphisms of bk be the one-dimensional representation where I say rho sub k of some B is B11 to the minus k power. And I can form the induced bundle, the associated bundle, and the associated bundle is GL2C crossed now over B, BK. That's a holomorphic line bundle. Everything inside is holomorphic. So that's going to be a holomorphic line bundle over CP1. And this is a hyperplane bundle to the kth power as a holomorphic line bundle. Now, let's study the holomorphic sections. Okay? Well, we have the holomorphic version of our grand tautology. So we have the holomorphic induced representations from B to GL2C, holomorphically induced from VK. And what is that? That's equal to wave functions psi from GL2C into the complex numbers, or VK, such that psi of G dot B is B rho sub K of B inverse psi of G, and psi is holomorphic. So that's the holomorphic induced representation from a representation of B to GL2C. So let's write out what that means. I've chosen this particular representation of the Borel. And so first of all, invariance under a B, which is of this form, implies that psi only depends on G11 and G21. Because you see, if you multiply this by this, so that's going to nicely be G11, G21, and then this is going to get screwed up in any, this you can make anything you want, because these are essentially anything you want as long as B22 is not 0. Okay, so psi only depends on G11 and G21. Now, invariance under, let's say, B11, 0, 1, implies that psi of, now use that identity there, implies that psi of B11, G11, B11, G21 is equal to this thing to the inverse, so that's B11 to the K, psi of G11, G21. Now, psi is holomorphic. Implies that it's a polynomial in G11, G21. Well, have you seen that before? Last time I showed that the holomorphic sections of the hyperplane bundle to the kth power can be identified with the vector space of polynomials in two variables which are homogeneous of degree k. So what I've just shown you is we found canonical isomorphism of the holomorphic sections with, let's call it h sub k, which is equal to the set of psi polynomials, say psi lambda u, psi lambda v is lambda to the k, psi of u v, sitting inside polynomials in, say, u and v. Okay, so now we've made contact with that observation, that the homogeneous polynomials, which are sections of this complex, this holomorphic line bundle over CP1, are canonically this holomorphically induced representation from the Borel to GL2C. Okay, so let's choose a basis. So I just want to show you a little bit about how you calculate the matrix elements, and then I want to connect back to the Wigner functions, and then we'll quit. Okay, so let's choose a basis. So first of all, set k equals to 2j, and define f tilde sub m of u and v to be u to the j plus m, v to the j minus m. where m is now going from minus j plus 1 up to plus j. So j and m can be half integer, but j plus m and j minus m are non-negative integers, so these are always polynomials, and you see they're homogeneous polynomials of degree k. Right, so I want to connect to the Wigner functions. So restrict this representation to SU2 inside GL2C. I mean, this is a representation space for GL2C, but it's still an irreducible representation when we restrict to SU2. So now G is going to be of the form alpha beta minus beta bar alpha bar with alpha squared plus beta squared equals 1. That's SU2. And let's calculate the matrix elements in this basis. So G dot Fm tilde. Okay, so let's evaluate it at U and V. So it's going to be Fm tilde. Now, you have G inverse acting on U and V. I'll let you figure that out. That's alpha bar U plus beta bar V, comma, minus beta U plus alpha V. So, by definition, that's alpha bar U plus beta bar V to the J plus M minus beta U plus alpha V to the J minus M on the one hand. On the other hand, the matrix elements, we might call them d tilde functions. They're not exactly Wigner functions. I'll comment on that in a moment. So on the other hand, we can write that. And how do you calculate these? Well, you expand these out using the binomial theorem. Remember, these are integers. So there's a finite sum in the binomial theorem. And then you collect terms to re-extend to get terms in this basis. And what you find is that d tilde j sub m prime m is the sum over s plus t equals j plus m prime, j plus m s, j minus m t, alpha bar to the s, alpha to the j minus m minus t, beta bar to the j plus m minus s, minus beta to the t. It's a mess. Now these are not quite the Wigner functions. They're proportional to the Wigner functions. But let's just look at the case where m right is equal to minus k over 2. And then we find that these d tildes, j, m, minus j, are equal to minus 1 to the j plus m, 2j, j plus m, alpha to the j minus m, beta to the j plus m. So, the holomorphic functions are corresponding to the lowest guy here. So we have, this is d to the k over 2 bar plus dot dot dot. If you like, those are your Bps states. Okay? Okay, now, very last thing. What about the fact that it's only proportional to the Wigner function? Where does that come from? Well, that's because I haven't said anything yet in this way of looking at the representation, the spin J representation of SU2 or GL2C. I haven't said anything yet about unitary structure. But geometry also gives us natural unitary structure. So you'll remember that last time I also pointed out that there's a Hermitian metric on this holomorphic line bundle, HK. So we can use that to define a unitary structure on the space of holomorphic sections. So h to the k over CP1 has a permission metric on it. Well, in the natural trivializations that I described last time, remember, so we had U plus tensor C, U minus tensor C, and we said S plus is equal to Z plus to the K, S minus. So in that trivialization, we said that a section, S squared, would look like 1 over 1 plus Z plus squared to the kth power times S plus of Z absolute squared, and similarly on U south, U minus. So therefore, if S is in H0 of CP1 with coefficients in HK, then introduce an inner product S with S, which is the integral over CP1 of this norm squared. This is a globally well-defined function on CP1 times the unit volume form on CP1. So remember, the volume form is I over 2 pi dz wedge dz bar over 1 plus z squared squared. Okay? So that makes this H naught into a Hilbert space. And now I claim the above, the induced representation for SU2 is unitary. Okay, so let's see how we do that. Okay, so to see that, I've been talking here about the space of homogeneous polynomials in two variables. So the first point is let P sub k equal the set of polynomials S of z of degree less than or equal to k. So that's sitting inside polynomials in z. Okay. I claim that there's a natural map from hk to p sub k, which is the following. You set S of z equals u to the minus k psi of uv, where you identify v over u as z. So you see a psi of u of v is a homogeneous polynomial of degree k. I can always divide by this u to the k, and I get various powers of v over u. Okay? And that gives me a polynomial in variable z of degree less than or equal to k. So we have an SU2 action here. If I demand that this is an intertwiner, then I'll get an SU2 action over here. We'll put it over here, and the resulting SU2 action is G dot S of Z is beta bar Z plus alpha bar to the K times S of alpha Z minus beta over beta bar Z plus alpha bar. Okay, so you see, if S is a polynomial of degree less than or equal to K, then I take a polynomial of this of degree less than or equal to K. I'm multiplying by this, so I always have enough powers of this, namely K, to cancel the denominators here. So this is another polynomial of degree, polynomial z, of degree less than or equal to k. So this is how the SU2 action looks in these local trivializations. So now we can check unitarity very easily. Again, I'm skipping some steps here, which are explained in great detail in the notes. So if I let z goes to z prime, which is alpha z minus beta over beta bar z plus alpha bar, then you can check that the pullback on the volume form is invariant. And you can also check that 1 over 1 plus z prime squared is equal to beta bar z plus alpha bar squared over 1 plus z squared. So what do? So you take this action. So you want to calculate g dot s comma g dot s. Okay? So that's equal to the integral over CP1 of 1 over 1 plus z squared to the k times g dot s of z absolute squared times the volume form. Now you make a change of variables. Well, first of all, you use the group action here. So this is equal to beta bar z plus alpha bar to the k, s of z prime absolute squared. Now you make a change of variables from z to z prime. You see here, you're going to use this identity here to see that this is equal to the integral over CP1 of 1 over 1 plus z prime squared to the kth power, s of z prime squared, and I told you this is invariant, volume of CP1, and therefore this is equal to S inner product S. So this is therefore a unitary representation, and so now so therefore, the holomorphic sections of CP1 with HK is a unitary rep spin J. And so finally, if I use instead of these wave functions, which are not properly normalized, you see these would map to z to the j minus m. Instead, if, again, this is a little exercise that you can do, if you use these, this is an orthonormal basis. And now, if you repeat the SU2 matrix elements in this basis are equal to the Wigner functions dj, m left, m right. Okay. There's more to say, but I'm going to stop. Okay, so I'll make a few remarks on reduction of structure group, and then I want to get to the last theorem of this course, which is the explaining that all bundles, all vector bundles, are pullbacks of these tautological bundles. And that's something called the Serra-Swan theorem, and this A lot of beautiful things to say there too, and we'll get as far as we can. All right, see you on Wednesday.